Okay, so welcome everyone. So it's a pleasure to have Jacques Sakarovitch among us here today. So Jacques is visiting Instructor for a few weeks. He is a CNRS researcher at IRIF, which is a research lab in University of Paris, Cité. And Jacques also wanted to visit us like in December 2022, but because of the visa regulations, finally he didn't manage to. He was visiting in Bombay. And I met him in 2023 summer in Paris, and I invited him again, and then we are very happy that this time he could visit us. So today he's going to talk about regular expressions and finite automation. Jacques, please.
Well, thank you very much for the introduction. Well, first I'd like to say I'm so happy to be here, and I'm very thankful for TIFR and Sebastian for the invitation. Sebastian has been very helpful. He helped me for the visa, for even for using my phone, and because I'm the kind of I have a kind of illiteracy in computing and these kind of things. So he said that I'm a researcher, but I'm more precisely emeritus researcher and at CNRS and emeritus professor at Telecom. And so I will talk today about I wanted to say, so I'm here for 3 weeks in room 207, if I'm and I'll be here most of the time, and I'll be very happy to discuss with anyone. I mean, I'm here most of the time, and you can comment and discuss something very happy. So this is the subject that we've chosen, Sebastian and I. Well, to tell the truth, transformation of regular expression into finite automata is something that it can be considered really a dull subject. It belongs to probably CS 101, or I don't know how you, instead the first course with computer science, you look at finite automata and regular expression, and you see it very clear. Well, I tried to make it a bit more attractive, more sexy than thing. In two ways. First, I'd like to give you my point of view on the thing, which is slightly shifted from the classical one, and also give you some new results, because even in this old subject, when there is room for new results. It's in total, there's a lot of things to say, and in fact, I don't know what you know, what you don't know. If I'm too slow, please just say blah blah blah. But if, on the contrary, I'm too fast without being aware of it, don't hesitate to ask questions, and if we don't reach the end, it's not so important. Okay, that's more. I mean, the travel is more important than the point we reach at the end. And if there is, if I'm on top of it, then well, either there will be another talk, or I will tell you in my room the last part of the talk. There is a general message that in all these things, which on these results that have been stated for very simple objects, when you try to generalize, you understand that things are maybe less obvious or more complicated or have more aspect than so. And I like to say that really truth really emerges from these attempt to generalize these results. Okay, so and it's more or less based on books. I've written one book on automata theory, but what I will say today is not there, because this has been written 20 years ago, roughly, and I've changed my mind on several things. And there is a chapter in this handbook of automata theory, but it also has been, even though this book has been published 2 years ago, I think. I've written the chapter 5 or 7 years ago, and also the new results are now in that chapter. Okay, more precisely, so there's a bunch of work on the subject, and some the last 2 is the new result being published in 21 and 22, which is not long ago. And finally, in fact, the impulse, all of the motivation for these results was the writing of software for computing automata, which is now available, and I will be very happy. I won't have time to show it now because it always takes a lot of time to introduce the software. But if you're interested, I'd be happy to also to show you this software privately, or we can make a small session for it. Okay, so the first part will be the description of what is called Kleene Theorem. Kleene, in the beginning, Kleene created this family, and that family called regular events and recognizable events. And he showed that these two families of events coincide. And for him, okay, that was enough, and he went to thing. I'm not sure, but I think that you have the complete work of Kleene somewhere, and this does not belong to this. It was something he did for the RAND Corporation in it appeared in the 66, I think. And it was first a report and then the written automata studied by edited by John Matlock, something like that, in 56. And but to understand it, and let's take some notation which are not the original notation. So I consider an alphabet, which is a finite set of letters, and so A star denotes the set of words, that is the sequence of letters, okay? And any subset of the primonoid A star is a language. Now we speak of even set of language. And I'll take the most common terminology, which is not the one I personally use. So you have regular languages, and you have a regular expression. I assume that everybody knows what regular expression, regular languages are. And we have also the set of automata over A star. I assume that finite automaton is anyway, I will show some. And for them being, I call because it's common. Recognizable languages, the languages that recognized by finite automaton, even though I'll show you that it's not a good terminology. Okay, so here we are. This is the set of languages, subset of A star. This is the set of regular expression, where one regular expression in, which denotes a language gap. Okay, and this defines the set of regular languages. We can say that the regular languages are those languages which are denoted by regular expression. Of course, another expression may denote the same language. On the other hand, we have here the set of finite automata of A star, and an automaton accepts or recognizes the language, of course, and this defines the set of recognizable language. Okay. Of course, another automaton may accept the same language. And now, Kleene theorem states that these two sets are the same. Now, how do we prove that? First conclusion, given an automaton, we show that there exists an expression that denote the language which is accepted by the method. Reverse conclusion. We should, given an expression, we are able to compute an expression, another method which accepts the language denoted by this. So altogether, this is Kleene Theorem. And now we understand that we can forget about the languages. It's a matter, in fact, Kleene Theorem is the union of two algorithms. And this is what I call a Platonic view. Because in Plato says that, okay, we are in a cave and we just see the shadow of real objects which are outside. In fact, we have no access to the real languages which are infinite objects. But we have these finite representation of these infinite objects, and we deal with them. Okay, so now if we come back, well, this is the classical Kleene Theorem as just stated. But in fact, one can think of non-free monoid. Okay, like I give the example of direct product of two free monoids. This will be the case of transducer, and I'm now giving a lecture thanks to Jacques on finite transducer. And it turns out that, well, the same result holds, even though what everybody would call the recognizable subset of them are not the rational and the regular, the set denoted by regular expression. Okay. And now, if we consider, and we shall see, I don't define precisely, but if we consider the languages with multiplicity, which is something now that was introduced long ago in the early 60s, but come back to interest because people. So the idea is, instead of having a word accepted or not accepted, you associate with every word a coefficient that may tell you probability that this word will be accepted or anything else you can do. So it's a richer theory for which you have also expressions, automata, weighted expression, and we have exactly the same result. And same in the case of, let's say, subset with multiplicity of non-free monoid. So the conclusion of this is, in fact, Kleene theorem, even though has been stated for free monoid, and in this case it makes sense to call the recognizable set regular set. It's not the case if you enlarge the scope, but what remains is that what I propose to call the fundamental theorem of finite automata is to say that the finite automaton, general as it is, has exactly the same computing power of regular expression. So that gives a scope which is much larger. It just says that now, if you have finite automaton is a finite directed graph and with labels, so this has a computing power, okay, and this is exactly the same thing as what you can describe with expression, regular expression. It's not somehow nothing different from what was said before, but if you just change this function, you understand that it's much more general than the beginning, and one should not take this recognizability, because recognizability indeed implies closure by complement or this kind of thing, which is not general.
So what does that K denote there?
Oh, K is the set of weights. It's a summarium. Can be a field, can be anything. It's just the general writing for the set where you can take the things. Okay, and so the finite automata or expressions or the series subset language. Okay, now so we have these two kind of algorithm from automata to expression, from expression to automata. Well, in fact, when you have an automaton, who would care to have the expression? Okay. You're happy when you have an automaton because you can compute, you can really do things with that. So, but I just give a glimpse of it, and this will help me to give some definition. But I don't want to treat really this subject. Okay, so this is an example of an automaton. This is an example which is in the many books. And this is one, if you compute regular expression from this automaton, one way, this is one possible result. And this is another possible result. So you see that expression can be very different, both in length, that would be somehow in size, which would be somehow complexity, and also look like alike. And so there is kind of course, well, it raises many problems. How do you decide whether two expressions are equivalent? How do you use, if you're an automaton, how you get the smallest expression possible, or this kind of thing, of course. But this is not the problem I want to talk about now, at least. I just use this to show, okay, this is an automaton to be sure that we agree on this. So it's directed graph, directed label graph, with two distinguished subset of state, the surfaces are called states, and I denote so the initial state, which are denoted by from now, and the final state, which I denote by outcome now. Okay, and by the way, this is if you replace A by 0 and B by 1, okay, this will recognize exactly the writing of numbers in base 2, which are divisible by 3. And but what I want to stress is that, in fact, this is the drawing somehow. It's very helpful to convey the intuition. But if you want to compute, if you want to prove things, I prefer by far to represent automata, to describe them with as matrices and vector. The initial set, the set of initial states is represented by here Boolean vector, okay, and here row vector. The final states like column Boolean vector, and the automaton is represented by the transition matrix. And the important thing is traversing the graph is equivalent to multiplying the matrix. This is this representation works and is useful. And in total, the language, the set of language of words that are accepted by an automaton is given by this formula. I multiplied by the star of the matrix X multiplied by T, and the star of the matrix X is the sum of all powers of X. Well, the star stands for, of course, and there is no problem of definition because with this model I've taken, that is, every transition is labeled by a letter, so the transition matrix will be, let's say, every entry will be linear combination, a subset, the union of letters, so it will be polynomial of degree 1, and so the power 2 will be, the entry will be polynomial of degree 2, and so on, so there will be no infinite addition. No problem. So Okay, and so the problem is to compute the star of the matrix. You can see this problem, theoretical point of view, from a practical point of view, and I push them always to the end. Okay, now this is the real subject.
So the previous thing, so if the automata was non-deterministic,
Or, in fact, this automaton is deterministic, but I'm not interested
okay,
particular. I mean, any graph, so can be non-deterministic. It's no special thing. In particular, if you have in view that you will generalize automata to non-free monoid or non-free monoid deterministic, it's no meaning.
so is it that, I mean, like if we
We may have
the same pattern showing in
Yeah.
multiple locations, but that might also mean that now somehow the same string can show up in multiple.
Exactly.
Okay, okay,
Absolutely.
okay.
Absolutely. And afterwards, we have to decide what we do when we add these things.
Okay.
We can add it as Boolean, that is A plus A equals A, or we can add in N, A plus A is 2A, and 2A is different from A. And we have all these possibilities, and this is exactly what we get to all about. It's to give this possibility to distinguish between the way we have. Hopefully, we will see that. Okay. Yes. So, thank you, actually. Okay, now this is the real subject of Michael. Okay, so the idea is.
So in the previous part, we didn't really go to a regular expression, right? Did we?
I would say that, well, the regular expression and the theorem, which has been not stated, is that the entries of the star of a matrix, every entry is a regular expression of the entry of the matrix. This is the theorem. And so, when you multiply this, you're right, I should have written it would have been more sensible. Thank you. Okay, so this is what we're about. And so what is the situation? So you probably heard, or maybe not on that way, of the Thompson automaton of an expression, or at least Thompson print. And you probably heard about the Glushkov automaton or the position automaton of an expression. I prefer to call it standard. And it's known that there is a relation between these two automata. And one of the two new results I want to present is another automaton, the net automaton, which is very similar to the Thompson automaton, and which has the same property that with closure. Closure means the Thompson automaton as well as the net automaton has the property or the drawback, I don't know what it is, at the feature that you have transition which are labeled by letter, but you have also transition which are labeled by the empty words. And that bring, okay, we know, you know, one should know that enriching the model, the computation model with that does not enrich, I mean, it doesn't make them more powerful, but you can, on one hand, you can compute sometimes more easily with them, but at the same time, we will see that it brings them tolerance. Okay, and now there is something which my experience is less known, but it's known, knowledge, at least we had a definition on an automaton defined by Brzozowski. In fact, I like the much more the variant defined by Antimirov, And I call it the derived term automaton. In fact, I don't like to give names to objects, people's names to objects, because you don't, it tells you nothing. Okay, and there is a very important property that, in fact, the standard automaton is sent by a morphism onto this derived term automaton. And the second new result is to understand better how this derived term automaton is built. So the first part of my talk, will essentially be this part. I hope to reach this within an hour, and the second part will be definitely, if you're not too tired, be able to get it. Okay, so let's begin very quickly with the Thompson automaton. What happened is that very soon after, some years, not so soon after Kleene's paper, so Kleene and Thompson, the guy from Unix, okay, he devised an algorithm for, so you have a regular expression and you search, that is, given a word you want to see where the word belongs to the language denoted by the regular expression. Unix is very much use of this regular expression, and it was a very important feature in very beginning of Unix system to be able to deal with the regular expression. Okay, so he published that algorithm in the communication of ACM, and well, afterwards, almost all automata textbook, they used that algorithm, the idea of that algorithm, to show that, well, they had to prove Kleene theorem, which is the theorem, and they always very often use this trick of Thompson to show that a language denoted by a regular expression is accepted by the finite automata. And for that, the point is that finite automata have to be somehow, for this proof, you have to put something in you have to add epsilon transition. And it's an artifact somehow. Afterwards, you say, okay, the artifact doesn't change, but you use an artifact for it. And somehow this is the basis of the problem. There is an artifact there. Okay, so this is drawing really appear in many textbooks that way, but I will, in fact, the idea, the true definition, I mean, most of the people say that regular languages, the family, is the smallest family that contains the finite languages, and it is closed under union, product, and star. And because it's the smallest family, so it's easy to show that they are exactly the languages that are denoted by regular expression, but their definition is that it's the smallest family. I prefer really to start from explicit definition with the expression, and afterwards it's easy to see, but of course it's so usually these drawings are used in the textbook to show that the languages are close by union, product, and star. And I use it slightly differently in the sense that, so I define automata for the base case, for 0, for the empty. So I define what is a Thompson automaton. And a Thompson automaton is an automaton where there is one initial state where nothing arrives, no transition arrives, a final state where no transition goes on, okay? and something in between that may have epsilon transition or transition with lattice. And you have three base cases with a Thompson automaton that recognize the empty set, the Thompson automaton that accepts the empty word, and the Thompson automaton that accepts the language reduced to one. Okay. And now what I define is operations on automaton. So it's slightly different point of view. I don't want to show that the languages are close by developed. I define operation on the automaton. And so if I have a Thompson automaton for the expression F and one for the expression G, the addition, the sum of the two automata is performed that way. This is a construction. And the same for the fire, and the same for the star. And this is the thing which is used by Thompson. And it's easy to see that this accepts the union of the language accepted by TF and TG. This accepts the product of the language defined by TF and TG, and this accepts the star of the language defined by TF and TG. So somehow, if we have this thing, so I start from a regular expression, and I can define that way the Thompson automaton of the expression, because I start from this, and using this operation, I get by induction on the expression itself a certain automaton, which is the Thompson automaton, and it argues that the language accepted by this automaton is the language denoted by the expression, so everybody's happy. End of the story for Thompson. Now, for the standard automaton that is defined by Glushkov or condition, so I will not take the definition given by Glushkov or the usual description. I will follow exactly the same idea. I'll first define what is the standard automaton. So the standard automaton is an automaton with one initial state that may be or not finite, finite or not. Okay. And no transition arrive in the initial state. Okay. And then you have the normal automaton with final states. But now it's a true automaton because there is no epsilon transition, only letter transition. And if I look at the way at the matrix representation, because of this form, we have something that is the initial state, the initial vector is 1 and 0. Okay? The final vector is, the first component, the first entry is C, then whether, which is 0 or 1, whether I is final or not, and certain Boolean vector. And the transition matrix is, of course, of that kind. The first column is 0 because no transition arrives in I. And so you have J, which represents the transition that goes out to finance the initial state, and F, which represents some other form, which is a square matrix that happens. Okay. And it's rather obvious that with the same formula as before, the language is given by this formula C plus J times F star times. Okay. And now on this standard automaton, I define operations, addition, product, and star. So if I have two standard automata, okay, this is the drawing of the sum, and it's easy to give matrix representation. Okay. And for the product, it looks like that. And again, it's easy to give the matrix description of that operation. Having the matrix description means that we will be able to prove things. Okay, not to say we see that, to have to look at the path of the. And for the star, it looks okay, it looks like that. And okay, this is the matrix description of the star. And every time it's easy to check that. I mean, the language accepted by the sum is the sum of the meaning of the language accepted. The language accepted by the product of the two automata is the product of the language accepted. The star accepted by the star of the automata. It's once again it's the star of an automata, which is operation of the automata. So we define now the standard automaton of certain expression. We start from the base case like before. And we apply this, and we apply the operations, and we get by induction on the construction of the expression, or by induction on the expression, if you want, or the formation of the expression, we get an automaton. Okay. And somehow this is the automaton defined by Glushkov, even though it's not the way he presented it. Okay. The point is that way is the way you implement. You can implement first, follow, last, blah, blah. But this is the fastest way. It's not only the most environment. I mean, in my case, it's the most mathematical definition of, more mathematical definition of the Glushkov automaton, but at the same time, it's really the most efficient implementation of the software test. Because it's something very closely. Okay, and so and it's folklore that the closure, that is, if you, let's say, correctly eliminate the epsilon transition in the Thompson automaton, more precisely with a backward closure, then you will get exactly this standard automaton. Okay, so which means that we have this. Yes, is that folklore or is that? Okay, so this is probably what I have described so far. And now we can go to new result. And for that, I have to go to an excursion to the weighted data and expression. I try to go as fast as possible, but I mean, I have to define the objects. And the reason why I go there, okay, I'm interested in weighted automata and thus weighted expression. And of course, we wanted to implement the algorithm to transform weighted expression into weighted automata. And the point is, well, it's easy. I mean, you see, a weighted expression means certainly that on top of the sum, product, and star, you have multiplication on the left and on the right by a coefficient. And it's easy to understand that for an expression, so you add, I prefer, you can do several ways. I prefer you just have for every element of the summary, of the weight summary, you add an operator, you multiply on the left or on the right side this operator, and you understand that if you put on the left or on the right of your Thompson automaton transition, which is one which is labeled by 1, but with the weight k, it will do the job. problem is that this generalization is not legitimate. And explain why. Okay. Okay, so, but probably I have to tell you in one word what a weighted automaton is. So I'll try to be as fast, but if something is not clear, of course. So here is the classical automaton. But so, and you see that it accepts all words that contains at least one bit. But now we can, let's consider the word VAB, and we can not only consider whether it is accepted, but the way it is accepted, okay, the computation. And for me, an automaton is a computation model. So I'm interested in the computations, not only on the result. And so it's easy to see that for the word BAB, I have two distinct computations. So in some sense, I can say that this automaton associated with the word BAB, two computations, that is the number 2, which means, in fact, the number of B, okay, that is in BAB. And more generally, this automaton so maps every word on the number of B. So this, the behavior of this automaton, if you think that you not only see what is accepted, but also count the number of computations. So it's a map from A star into the summary of natural integer, non-zero, non-negative integer. Okay. And we can write that it's a series of A star, and I can write this behavior as a formal sum series. B plus AB plus, okay, you see that there is no empty word, there is no A, B, and there is no AA, because that's no B, 0. This is the way of formal sum, it's formal power series on non-commuting variables. Okay, but if I have this at hand, I can make the game more fun. I can put coefficients on the transition. And now I have two, I still have two computations, but I have to define what is the weight of the computation of the path. It will be the product of all coefficients I see along the path. And the weight for one, it will be the sum of the weights of all paths which have this word as label. And it's exactly the same thing that we have done before for counting the number of the computation. Just before, all the coefficients were 1. And you can add things at the beginning and at the end also. Okay, in this case, so for BAB is 5. And you can understand that if you replace B by 1, A by 0, it's the value of the, in the Boolean, the writing in the base 2, this thing. Okay. And so once again, so this automaton maps every word W in what I just described. So it will be a series again, and I can multiply that. Okay, B plus AB plus 2PA, because PA represents 2, and so on. So, last example, I can go outside of
The previous one, the ones where the labels are not, the weights are not mentioned, they are 1, right?
yes,
Okay.
yes, yeah, it is included. Well, if it is the identity of the surname, I don't write it, but in certain case, I have not put this example as an example. When you deal with the mean plus surname, for instance, it's very tricky that the neutral element is 0, so you better to write 0. Okay. Okay, let's see this example, now we are, now the seniorings are integer, but not necessarily positive. Okay, now we have three, for the word BAB, we have three possible computations. Okay, and we use the same rule. It's general rule for weighted automata. And so for BAB, we have so the coefficient of this part is -1. Okay, and it's not difficult to see that it's the number of this minus the number of. And so now, so this automaton, it maps every word to the difference between A and B. And so it's a map from A star to Z. So it's a series, the Z series. Okay. And this is so. Okay, that will be our definition, and we can comment. But it's interesting that when weighted automata, which were defined in 61 by Berger, and were at that time they called these numbers, in fact, not the coefficient, but the register exactly in the automata of deal. No, algorithm. Okay, so in fact, the people who were looking at this were not interested in the coefficient. They were interested in the support. That is, which word will have a non-zero coefficient? And you see that in this case, the word which have a non-zero, the set of words which have a non-zero coefficient, it's not a regular language anymore. When you are in N, of course, it doesn't change. But when you are in Z, and if you are in a field, so the first motivation for this weighted automata was not to associate weights to words, that now this is the most interesting thing, but to define more powerful machines. But this direction of research didn't prove to be very fruitful. Okay, this is not okay. And now I'll show you why the Thompson construction is illegitimate. Okay, let's consider a Z expression, A star minus B star. So A star is this, A star minus B star is this sort of thing, where we do not have antidote. This is a series with valuation 1. Okay. And this is Thompson automaton, so step by step. And you see what, okay, to have -1 which is like this. By symmetry, it's not important. Okay. And the problem comes if you look at the star or this expression. This expression is valid in the sense that you can take the star of this series, of course, because it has valuation 1, so the square will have valuation 2, the cube will have valuation 3. What do you mean? Valuation is the degree of the smallest degree of a word which has a non-zero coefficient. Okay. Which means that if you look, so the star of the series is the sum of all powers. Yeah. And so it's obvious that if you take the star, there is no problem taking the star of a series with positive derivation, because any word of length, the degree is the length, and will appear in at most the n first power of the series. Okay, so the sum is well defined. The problem is when you try to have infinite sum, as you know. But at the same time, if, for instance, you know that if you sum the power of 1/2, if you're smart enough, smarter than Zeno, you can define topology and you can prove that the sum of the power of 1/2 is 2. 1 plus 1/2 is 1. But so it shows that there is some difficulty. But here we don't have even to enter this. Okay, this obviously the star of this series, that is the star of the series denoted by this expression exists, so that somehow we can consider this expression, which is valid since it gives a result. Okay, so I can write it down. The point is, this is the star, the Thompson. And now you see that within this automaton, you have secrets of epsilon transition. And even if we don't go into the theory of validity of automata, you understand that this will not going to work because certain world will have an infinite number of paths because you have this loop and after you can put something. And of course, you'll be unable to compute what is the multiplicity of A, for instance, because you have one thing like that and one thing like that and so on and so on. So you will 8 plus 8 plus 8 plus 8 number of times. And the fact that you have another circuit with -1 doesn't help because you have 8 minus 8 plus 8 minus 8. You don't know how to can. You know that this is not summable. So it means that the Thompson construction doesn't work for expression with multiplicity, at least in the, in fact, as soon as you have 0. I mean, you have an element that can add to 0. Okay. So here we have to make the theory of this.
So in the previous thing, if this was the automata that is the weighted automata that is presented to us, it's not even clear what the weighted expression corresponding to the automata is. I mean, so previously it was always the case that given an automata, you always had an expression.
Yeah.
I mean, given any automata, there was always an expression. But if you have automata that have epsilon transitions on them, it's just that there is no legitimate expression you can write down by just looking at.
I don't say that.
Oh, okay. So for that automata, what would the expression be? I mean,
for that automata. No, in fact, I have not spoken of this side of okay, from automata to expression. From automata to expression. Okay, and this one it will be A plus B star times
he asked me
minus
no. In the example that you showed for non-validity, the next slide.
the next line.
The next line.
Yes, but it was not an automata. It was an expression. Okay. Yeah, I come. Now, I just finished to answer your question. A plus B star. This is an expression for that.
For this. Okay.
Okay. No problem. Now, your question is, it's different. Your question is whether there exists. You know like that. I thought that I should done it, and I did not. Okay. Your question is whether there exists an automaton that accept let's say recognize that series. This is your question.
No, I am in fact asking the question that, so if we look at the star, I think it was a couple of slides later where there was a path of just epsilons.
The cycle.
There was a circuit completely made up of epsilon. So given this automaton, if someone gave me an automaton and asked me to build that, the power series expansion, it's not even clear what that is supposed to be here because I don't know how many epsilons.
Okay, from an automaton, you can always compute an expression. Okay.
So it has to go via, okay.
Yeah, but this is completely formal. Okay, it's formal. You have an automaton, and in fact, you don't think about this. You can replace every transition, every label by a certain letter. Okay, you change it, you compute the expression, and then you replace back the name you have given to the real thing. Now, what will happen with the expression you will get? If you start from this automaton, you will get an expression which is not valid. And I'm just about to define what the valid expression is.
Okay.
Okay? Yeah.
So in the definition of, what did you call it? The weighted expression, you had a multiplication for every path, and then you sum over all the paths that take you from the initial state to the final state. What if I require that you only sum over paths that are simple, in the sense that they do not involve the same vertex twice?
This is not the computing one. I mean, an automaton, well, I mean, you will recognize only finite path, and the idea of automata is to have a finite representation of infinite objects.
Sorry, not simple is not the right word. I want to sum over paths that do not have epsilon cycles.
Yes, you're right. The epsilon cycle, not good. But at the same time, what if on the epsilon cycle, there is the product of the, just what I said before. Suppose that you have this automaton. Okay, so this is an epsilon cycle.
I see.
I mean, if you want to be consistent, you want this to be equivalent to this automaton. But this is what, I mean, this is the problem of what is the validity of an automaton, whether we can decide it or not. And this is another topic. But I agree, it's really a question. Okay. Okay, so these are the classical regular expression. And now for the weighted expression, we have a bit more, we have these, I mean, for every k, we have these two operations. And for every expression or definition, we have what is the language of the series denoted. Okay. So all this makes no problem, but only this. What is what is the, how can we define the series denoted by the star of an expression? We have to define the star of a series. So I'll try to be as quick as possible. So I'll give you just the result. So we consider the constant term, that is the coefficient of the empty word. Okay. Every series we can write it as a sum of a proper series, that is a series which is of valuation at least 1, and the empty word with coefficient, this constant term. And these are definitions. And beside this, I said that an element of the weight summarian is starable if the sum of the power is defined. So, which means that to be complete, you have to define topology, blah, blah, blah. But we suppose that all this is done. Now, there is a theorem which then, if K is a strong summarian, what it is, then the series is starable if and only if its constant term is starable. And in this case, we have a formula. Star of the series is, so the star of the constant term multiplied by proper part. We take, this is a proper series. You can take the star of this and we multiply by this. Well, okay, this is very easy. The point is, I was a bit, so in fact, I don't know if this is true in general. I cannot prove it. And there is good reason to think that it might not be true. But so you have to take the least hypothesis possible so that this is true. And strong summarizing just means that, I don't go into detail, but that is the product of two summable series is a summable. This is true in R, in C, in, okay, this is one of the very, you find it also in calculus, not one, but it was in the Schwartz book, Method Mathematique for Physicists, for instance. It's one of the things at the beginning. Okay. And in fact,
but
there exists.
There's a finite product of two sums.
Yeah.
Not, you're not the.
No, I have one series.
Mhm.
No, I have one family, okay, which is summable, which means, okay, the definition,
Yeah.
not topology, but it's summable, exactly, absolutely summable in R,
Yeah.
okay? And the product of two summable families, so you define the product as the family of pair, product pair. This is a summable.
Okay.
Okay. And recently, with a friend, I first went to see mathematicians, and I posed the problem. I have this problem, and many of them told me, "Oh, we are not interested in summary. This is not a structure which is interesting." And okay, you can complete your sentence. Okay, but I have a friend at the telecom, and he's very smart, and he built a simulation which is not strong. Okay, everything, it's even a ring. That it makes it. Of course, it's a bit weird. It's kind of monster, but okay. It has all the properties you want. It's a ring, it's an algebra, it's not strong. We don't know whether in this ring the star is different physics. But okay, so strong submarine, it's a sufficient hypothesis. It covers all what we need, and okay, I'm safe somehow. And now the definition here, it's okay, the star. If the constant term of the series is starable, then the star on the behavior of the star of the expression is. So you may ask, wait, yes, but this doesn't tell if I can compute that, because this is the constant term of the series. The point is, in fact, it's very easy to compute, and it's not surprising, it's very easy to compute the constant term of the series as the constant term of the expression. We compute it on the expression. So that's very easy. So you can decide everything. And now I can explain one word, how we build the new automaton. This I got from the Thompson automaton, and I call it the net automaton for some reason. Okay, so the base case, you see that the difference is, in fact, what happens, the initial state will be as a final state, the constant term, okay, which is the coefficient of the antibody. So this is for, so it changes only, of course, the automaton which represents which accepts the anti-word, and for the multiplication by k, you just add this, it's nothing different. For the sum, in the same way, the product is slightly different. Okay, this is the form, but this is the way. And now, this is for the start. You see that there is no, what we have deleted that transition, which was in fact indeed the problematic transition. Okay. Okay, so there is no exclusivity in this net automaton. And the theorem is if the transition, the expression is valid, that is, you can compute the constant term of the expression, then the automaton is valid. And so what happened, to answer the question, if you start on Thompson automaton, which is not valid, the expression will be not valid. And this is not surprising. You start from an automaton which is not valid, whether it's Thompson or not, you get an expression which is not valid. The reason why I said that the Thompson construction is illegitimate, it's because it started from an expression which was valid, and because of the artifact in the Thompson construction, you get an automaton which is not valid. And certainly you don't want that. I mean, the construction you want is, from a valid expression, you want a valid automaton. Okay. And so this is what is achieved by this. Okay, this is the Thompson automaton, and this is the net automaton of that problem. Okay, so here we are. So I don't, so I've been big longer than expected, but I can go on. I don't want to bother you, but it's really up to you. We go on, or we stop 5 minutes, or whatever we want.
So, I mean, I think in the announcement it was for 90 minutes, and then we prepared for 90 minutes. So, okay. So I think we can finish in maybe another 15 minutes.
I'll try.
If you want.
Okay, just one thing, it's still about this net automaton. It's something that we, so of course we implemented this because we wanted to be able to have something like the Thompson automaton in our system. And I don't know if you know what the star normal form of this expression is. You heard of it. So this is the transformation that goes from, sorry, it comes from 92. So it's a law. The idea was of Woodman-Kleene was given an expression. Now, if you start from any expression, it might be the case that the computation of the Glushkov automaton is not correct. Maybe cubic. So her idea was to transform the expression in such a way that after with the computation of the Glushkov automaton will be quadratic. And the idea is to, I will not go into the details, but there is no sub-expression. If a sub-expression contains the empty word, it is not star. And so you have rules to transform, breakers will be an expression. You start from the expression and you transform it into an equivalent expression, which has its property, which is in star normal form. Okay. So for instance, if you start from A star star star, the normal form is the star, and the most somehow striking transformation, if you start from A star to star star, this is what you get. Okay, so now on an automaton with epsilon transition, an epsilon transition is superfluous if you can somehow mimic this this transition using other epsilon transition. Okay. For instance, here, this transition is superfluous because you can do it. And this transition is superfluous because you can do it. So now you take an automaton with epsilon transition and you erase all superfluous transition. Okay, so and it's obvious that if you have no secrets of epsilon transition, then what you get is equivalent in this model. And the theorem is surprising that now if you take the net automaton, you take out all the superfluous transition, and you get the net automaton of the star normal form, which means that it was not something that nobody had imagined that there is an automaton transformation. It's not on the expression, but on the automaton that somehow mimics this. Well, in fact, this theorem is not exactly, it's not formal, but it's essentially, I'll show you why I say it's essentially. Okay, here we have this automaton, and okay, this is when you go in the board. So you understand that I will define something slightly different from the net automaton, but which is almost net automaton, obviously equivalent, and in this case, it would be n prime instead of n. It's essentially the same thing, and in this case, the theorem of reduction. Okay, I want to say a word of the derived term automaton. Okay, so to get to this, and I think it's worth just to show what is the original point of view and affiliation. Because so this construction is based on the fact that the language is regular if it has a finite number of left quotient. That is, so for any language, if you take any language L and any word U, you say the quotient of L by U on the left is the set of words such that UV is in the language. So if you think that if you compare free monoid in the free group, so you take the inverse of U, you multiply, and when the remaining is only a word L, it's exactly what it is if you are able. So this is the quotient. It's a real division because you multiply by the inverse of. Okay. Okay, and the characterization of it is a characterization of recognizable languages. So they have a finite number of their questions. And the idea, okay, and this is, and the idea of Brzozowski, what Brzozowski wanted to do is, I told him it was very interesting. The problem is, if you want to prove that two expressions are equivalent, the only proof we know is to transform the expression into automata and check whether the two automata are equivalent. And he wanted to have that proof of equivalence staying in the world of expression. I think it's not possible, but this is what he wanted. And to do that, he invented something quite interesting. So this is, so given an expression E, you divide, so that denotes L. He had a definition of what is the derivation of E by A with respect to it, which has the property that the derivation of E by A is the quotient by A of the language denoted. So you can go on and on and on, not necessarily exactly, but to some extent, you're able to build a finite automata.
So can you go with that? So initially, E is an expression which is now associated with the language we started off with.
Yeah.
Oh, I see. So
At every step, we can do, I mean, it's just a sketch. It's just to give the idea. So we have expression and we derive by all letters. So we get expressions that recognize A minus 1 L.
So in some sense, so for every state of the automaton, the language associated with it is like as if that state was the starting state. Is that right?
The point is, this is the minimal automaton of a language. This is the way you build the minimal automaton of a language. Since there are a finite number of quotients, so there is a finite number of words, okay, that gives you different quotients. And so you go from one quotient to the other in that way. This is before speaking of any expression. Okay, you start from a regular language. You know that it is recognizable, and then you have this minimal automaton this way. And now you start from an expression, and the idea was to mimic this operation of quotient at the level of expression. And this is what Brzozowski did.
Why is that? So on the previous picture, why is the loop there and the loop there not on this?
Because there is no reason why the derivation, I put, these are different expressions. There is no reason why the quotient of the derivation of this expression by B, which is this one, is the same as this one. The expression itself is different. Okay, so as an expression, it will be in the world of expression, it will be you will see,
But then
it's even more complicated.
But then why does it go back?
Well, because I assume that the derivation by B of this expression is equal to that. This is what to that expression. Maybe it will be clearer with this. Okay, so this is the definition of the derivation of an expression. Okay. And you see that
Brzozowski derivation is those classes that
what are people derivatives? Okay.
no, in the previous slide, the quotient classes are very similar to Michael or
Yes, they are. It's not similar. They are. But what Brzozowski did, he built it. So this is a formal definition. You have an expression, you have a letter, you derive, and you do it by induction on the expression, you get something. And you have this, and the main point, tricky point, is that the derivation of f plus g is one expression which is the derivation of f plus is an operator of the expression. So this is one expression. Okay. And now the point is, you want this the set of expression you get to be finite. And in fact, it's not true. It's not finite. You have to put in some axioms, associativity and commutativity and hyperconvergency. That is of the addition. So if you have two expressions plus, E plus E, you say, oh, that's E. Okay, so you understand that computationally it's rather heavy. And moreover, we get deterministic automaton. Because, and a deterministic automaton, might maybe very big compared to the stuff. Okay, so but anyway, this is theorem by Brzozowski. Okay, so he somehow, he lifted the operation of quotient from the world of languages to the world of expression. And that was the first. And now came, this defined derivative automaton. Now came Antimirov, and what Antimirov did was he replaced the plus here just by a union. We have an expression, and the derivation may give us two expressions. Okay. And let's imagine, you have to deal with the derivation of the union, but you do it very naturally. It's the union of the derivation, blah, blah. And then, without any use of axioms, it's fine. And it's a small number.
Sorry, what would a star of a union be?
I'm sorry?
If we have a union expression and we take a star on top.
No, we don't take. No, we have an expression, and this formula tells you what is the derivation by one letter.
Okay.
Okay, so you start from an expression and you get a set of expressions. Okay. Pieces, bricks.
Yeah.
Okay. And the miracle somehow is that you have a finite number of such pieces. And in fact, not many. Okay. So this formula, without changing, so it was, and in fact, less than the number of letters in the expressions. That is, now if we go back to our drawing here, schema, so what we have, so now the derivation by one letter is a set of expressions, and the union denotes, the union of the language denoted by this expression is exactly the expression, the quotient of the language. And of course, so we have an automaton. So what we get is an automaton, which is not deterministic anymore, but which is much smaller, which is indeed smaller than the Glushkov standard automaton. And in fact, there is a morphism on one field, which is another thing that it is small. Okay. So in one word, so the point is, now, why I said that the recognizable set of M are not the regular set, it's because the recognizable set can be defined by the quotient. And it's not true that there in a non-free monoid, the quotient of a regular set or rational set are finite. So you cannot build this minimum deterministic automaton. It's not, does not exist anymore. And so, okay, here we were, but if we want to do the same thing for an automaton M, for a monoid M, which is not frame, it doesn't work. And somehow the other result consists in showing that indeed, yeah, I don't want, what is this? Okay, never mind. Oh, no, it's almost the proof. It's still possible because, in fact, what was called this derivation and related to quotient has nothing to do with it. It's in fact, it is another construction. But it will take some more time, and I don't want to be heavy. I'm sorry, I'm not being able to make it in 90 seconds, but in 90 minutes. I'm not in 90 seconds.
Any questions?
So just, I mean, I don't even know if this question makes sense, but I mean, are there situations where these sort of quotients are extended to, I mean, rather than taking a quotient with respect to a letter or something, where you take a quotient with respect to a language? Are there no?
No, I mean, in fact, the quotient is an action of the free monoid over the language. Okay, so then you take the letter and then you take the quotient by letter, and then by letter, the same thing as taking the quotient by the word AD, and take the quotient by AD. Now, so afterwards, if you take the quotient by language, what will you do? You will take the union of all the quotients here for a word, or on the contrary, the intersection. It's not clear to me. What is the quotient? No.
I was just wondering if notions like that have been studied, because I don't know. I mean, in the field I work in algebraic complexity. So there's a very classical depth reduction sort of results, where the key insight was basically something like the derivative, but you're doing the derivative in just one direction. Basically, the derivation operator that you had written down is exactly what works there. Except there they work with, you're not deriving with respect to a letter, but you're deriving with respect to a different polynomial or something. So I was trying to see if there are analogs of that in this world.
No, I cannot answer.
Okay, but so, yeah, I'd like to chat with you.
No, well, it's
yeah.
Question.
Okay, so if there are no more questions, then let's thank Jacques for the talk. So on 25th, he's also giving an essay colloquium just 2 weeks from now, like on Wednesday. Thanks. Thanks.
You'll end the stream and